Sure. Okay, so good morning, everyone. So nice to see at least a few of you come over here already this early in the morning. So as there's quite a bit more focused presentations later on the track, so I was hoping to maybe give a bit of more of a overview of what sort of different things we've seen happening in Edge AI, what sort of like individual aspects does that mean and contain, and perhaps like what do we see coming up going forward over there. But before going sort of more in depth to the topic itself, so maybe give a bit of a brief overview of what Silo does, what Silo is, for you to also get the context of the rest of the presentation. So first of all, so what is Silo? So we are a services company. So while we do have certain product work of our own, but primarily we do professional services. That means rather code to the editor rather than PowerPoint to the wall. So we actually do the stuff ourselves all the way end to end. And while we are sort of 5 years old at this point, we've grown rather rapidly. So right now around 240 people in the company, and more or less not only the largest in the Nordics, but sort of top 3 pretty equally within the whole Europe at this point. One specific thing that we've always been focused on as a company is really to pay attention to the state of the art of AI. And that's why we also so focused always on hiring a lot of PhDs. So more than half of the company actually do hold PhDs. Some perhaps not machine learning, but physics, math PhDs on the side as well. And well, we are a Finnish company who started from Finland. Now already pretty good stronghold also in Sweden and Denmark at this point. And there's also a bit of activity already in the local Switzerland, although over here, although not that much yet, but definitely the Central Europe is something where we are heading further in the long run. So the really briefly of what sort of has been the journey. So 5 years naturally. The founders are pretty strong bunch. So there's a Nokia CTO, former one, and then also a Bittium founder who was then exited to Continental for more than €1 billion a few years ago, and then they put together Silo to really focus on, okay, what does the overall industry need to go and become more AI driven in the future. The key reasons why people generally choose to work with us are really pretty straightforward and simple. So the first thing that I already mentioned is the state of the art. We really see that that's a really strong thing, that we can actually not only talk about the things with customers that, okay, this is what you can pick up from these proven libraries that everyone can use, but what we can do instead is that we can actually go and put things into production that was only research publication a few months ago. So we've also had projects where we actually pick up DeepMind papers that are sometimes rather complicated to actually re-implement and put into production, and we've done actually those rather successfully several times. The other point is really what we see overall in AI, and especially when we focused on this sort of more of a cutting edge of AI, is that it's not enough just to have a bunch of people to go and do the code. And I think Edge AI is a good example of that there's a lot of complexities you need to keep in mind. And that's why it's not just about let's do the implementation, but actually understanding the problem, defining the problem, understanding, okay, who do you need to have in the team from both of us and from the customer is like really critical piece of the overall puzzle. And then the last bit over here is actually a total example of what does it mean to do Edge AI, is the end-to-end capability. So doing the algorithmic bits, while let's say like for us as well, the background of us is really coming from the algorithms, that's sort of where we're really strong. But in the end, like especially when you go to Edge AI, the question is, you can't just do the models. because you can only do the models if you really understand, okay, what is the computation on top of which you're running things? How are you actually going to operate it? Well, what is the data processing in between and so on? And that's actually something I'll go a bit more into a bit later. So just a final brief on the expertise. So naturally, it's really, really broad. So machine learning, what does it mean? So all sorts of things on computer vision, natural language, time series, tabular, a lot of that. But actually, a really big piece of what we actually do is not so much related to the cloud, but actually a lot of it, perhaps half of what we do is really edge AI on embedded systems, on IoT systems, on various kinds of things. Also a bit of mobile, although not that much in the end, actually. And the kind of setup in terms of use cases that we've done in the past, so there's just like a tiny selection of what we've done, but it's really rather wide, touching sort of all different industries in the world, so and really broad-based approach to all things AI. So then, if we move to more into the actual topic over here, so the edge AI, and then the question is, okay, why is edge AI? I think like the abstract that I had for the talk was also that, okay, what is even edge AI? What does it mean? And like, is that something that we can actually keep on talking in the future? And one of the big theses I would have for edge AI is that there's no edge AI, because it's just a huge umbrella term. Just as well you could talk about AI, but there's like incredible amount of different technology and methods that go underneath that term. And the same applies to edge AI. So there's so many different technological contexts that you really need to understand rather much in the detail. What are you actually up to do something tangible with that? The second point is that while perhaps like if you really go and check, like edge AI hasn't been that much of a headline topic, even in the research side, more than a few years perhaps. But actually, I think that's also a good example of how things generally work in AI, so that things really move from research into production in really quick terms. So I think there's the whole track is full of those examples where something that was just working on my laptop in a lab in a way, at this point, then 6 months later, it's actually somewhere in production in a real product. And then the other point is really, as I mentioned, so the end-to-end. So it's all about the different aspects of the overall tech stack that you need to keep in mind for the edge AI to work. So what are the reasons why in general edge AI is getting into use? A bunch of real-world examples. So basically everything that I'm talking today is actual project examples that we've done in the past. And generally edge AI is just answering the question like, why can't I run this thing on the cloud? And then there's a whole bunch of reasons why that isn't the case. So one thing is of course like if it's illegal to put stuff to the cloud, there could be various regulatory or private contracts that say it's impossible. So for example, here it's a personal protective equipment case where there's natural privacy questions on can you actually move the data where there's recognizable humans in the pictures. A second example is too expensive. So I think the microcontrollers, the TinyML that's coming up later here is a really great example. So for example, we've done some cases where, for example, there's a air quality sensor. It's an 8-bit microcontroller, and well, there's actual chemical reactions going on, and the quality of the sensor is degrading constantly. So what you can actually do is put ML into running on top of the MCU and improve the quality of the results. So naturally, that would be rather ridiculous idea to try and move that data anywhere. There's way too much of that. The third point is reliability. So this is something perhaps that really comes up in factory settings. So when you go and have machine learning do safety critical things, you go and have machine learning do operationally critical things, you can't have the factory go offline because there was a bug in the machine learning code, for example, then those are naturally things where you can't trust the network and you need to have things running on the edge by the production line over there in some box, one sort of or the other. And the final bit is just things where it's impossible to use the cloud. So there's a lot of environments where actually there is no network. It just doesn't exist. And hospitals have been one good example. So we've done patient monitoring for patients that fall down, can't get up themselves. The whole hospital is air-gapped. There's 0 connections coming in, 0 connections going out. So whatever you actually have running over there, it really needs to work within that context specifically. So the pieces that I mentioned previously about, okay, what does Edge AI consist of? What are the different building blocks over there? Is these 5 things. So you need to really pay attention to all of them, and the questions that you can sort of place to the use cases, they're always the same, no matter what is the context, technical context, what is the use case. But then again, depending on the use case and the context, the answers you get or you need to get for those questions are extremely different in terms of what does that entail for development. So for hardware, it might be everything from understanding, well, what is the right choice of the AI accelerator hardware in terms of, let's say, memory bandwidths, specific architecture, fit for models, power budget, and so on. But there's also things like understanding what is actually the architecture, what are the different chipsets that are possible to be used, and where should you place your compute on. So there's been several cases where you really need to pay attention. How do you split the model, and you spend a certain piece of that computation on that chipset, and then you move the data to another chipset and run the rest on the other piece of hardware. And that is also related to things like static tuning. So if you really have a sort of really good low-level compiler understanding of how will this matrix computation code actually turn into hardware language, then you can go and do rather interesting tricks on reducing, for example, the memory pressure that the model computation puts on the overall solution. Data questions are also another thing. They are rather different on edge than they are on the cloud, and they are rather different on different contexts on the data on the edge as well. So whether it's about dealing with competing applications for quality of service, or simply understanding that the number of different sensor interfaces coming into the device and making sure that they actually work, and you can actually go and pick all the data that's coming in and use it. Those are rather common questions. For software, it's naturally, you could see it as a rather broad question of all the software that will end up in a solution. But the real question there, what do you need to keep in mind when you go to the edge, is how does the reason that you have a certain specific AI model in mind to be implemented there, what sort of decisions you need to have for the surrounding software. And then again, what are the things when you go and decide the software architectural questions, how does that affect the decisions on your model selection? So there's quite a bit of interaction all over the place across the stack, and that's why really often it's a question you need to have AI expertise infused in all of this development on every single layer over there. For AI models, well, naturally there's the model itself, But it's much more of a question. So that's sort of an obvious thing. But the big question when you go to the edge is that there's quite a bit of constraints that the hardware and the use case often, at least near real-time use case, puts on, okay, what is actually the model? How much does it produce memory recycling that might produce latency issues? How do you go about them? How do you modify the model compute code to avoid the sort of latency jitters on a wrong point in time? And maybe a second reasonable question is again, well, if you don't have a full cloud MLOps stack running on the edge, naturally you can't really monitor all the different devices you have running around the world, then how do you automatically still make sure that, okay, when the data changes, there's data drift and things start really going bad for the model results, how do we make sure that we can actually catch it up and can actually do some meaningful fixes for those situations? So a few examples, concrete examples of how do these specific questions that we sort of keep in mind going to the edge, how do those relate to real-world use cases? So there's a few ones over here. So the first one is on chemical emulsion and understanding what is actually the mixture in the tank and how can you actually manipulate it. And this use case was built on an oil field, so it's rather remote, and everything needs to run next to the equipment actually over there. And there's a bit of a small mini cluster, so there's quite a bit of compute available, but nevertheless, there's also quite a bit of different models and software they need to run over there. And that takes certain limitations of what kind of machine learning you can actually go and run over there. The second bit there is there's quite a bit of messiness in this field setup. So there's a bunch of engineers going to the field. They go and set it up, all the sensors, all the computers, all the software and so on. And there's a lot of mess. There's a lot of things that are different from one time to the other. And how do you actually make sure that all the tooling around the machine learning also turns the final solution into something that is actually manageable across all the different examples. On software, it's really a customization once again, so deployment specific. Not a single deployment is the same as the other one. So it's every single one has a different setup of sensors, different configuration of the overall hardware. How do we make that once again easy to understand? And the final bit, perhaps picking up on the operators. Naturally, it's about efficiency, about people operating the whole system where they don't have machine learning training, but they nevertheless need to be able to do somewhat deep maintenance jobs on the overall software once in a while. So once again, it's a big focus on how do you do reliable tooling for the people managing the whole setup. A bit more in depth into the embedded world. So with the industrial camera setup, we've been building a whole design end to end, all the way from the hardware selections, chipset selections, placement on computation, to the models themselves. What kind of what is the tech stack to run AI models within the cameras themselves from now into the future? And there the big questions has really been that, okay, if we decide the hardware now and then we're going to build the models 5 years later, then how can we actually make this decision? How can we guess what sort of computation do we need to have there? How many different models? What is the computational need? What kind of models those are going to be? What do we not want to run in hardware? What do we want to run in software? And since we don't know a lot of these answers yet, how do we build the whole stack from hardware to software in a flexible manner so that we can actually go and fix these things later once we actually do have the answers in place over there? So there's quite a bit of questions running all over the place on for example, on data processing. It's a very heterogeneous case. There's 4 different chipsets where you can run one kind or the other of AI code and software code. Which piece of chipset is always the best place to do a certain piece of computation? For example, if you have a convolutional net as a simple use case, what layers do you run on which chipset? There's actually different computation, different memory requirements on different parts of the flow. When do you move data from one chip to another? So I think overall, what was pretty clear already is that the big question with edge AI is really this end-to-end nature. You can't really design the hardware without understanding what the AI is going to be, and you can't really design the AI without understanding what is the hardware the models are going to run. And the same question goes all the way through the stack, similarly, for example, to operations, understanding what is it actually going to look like when it's running for real users. And the big reason there, why is it so, is that AI, first of all, it's really resource hungry. It takes a lot of compute memory and so on, but also that it's basically always still the most immature piece of the whole technology stack. And what does that basically mean is that if you want to actually go and take all the potential of modern AI models and put those into actual real-world use, then all the other bits of the stack, all the sort of like more mature ones, where we also sort of already know how to manipulate them and still keep them reliably running, those need to bend and be flexible and fit the needs of the models themselves so that the overall solution can actually work and we can actually leverage the potential of the models themselves. So what does that then mean is that if you need all the different parts of the stack to bend, then that means that you need to have the AI expertise in place when you do the design of all these different pieces of the stack. And that is the simple reason why you really need to have the AI expertise itself infused in all the different pieces of the development flow. And really edge AI is the living proof. This does apply to the cloud world as well, but even much more so for the edge world. So how do these different things interact? So for example, looking into AI and compute, there's a few examples here. If you have sensors, for example, I think already mentioned, it's a question of how do you fit the specific machine learning model, how do you choose machine learning models, how do you tune them to fit a specific hardware architecture and a power budget that is there. But that is only, the one side of the question, because there's also this other moving part of the hardware. You can actually affect the hardware choices, and this case was a rather good example where there was a number of different evaluations that we made. Okay, we have like 3-4 different hardware options, whether it's small ARM Cortex, or maybe just going really deep down to the microcontroller world. And all of those different hardware options give you different alternatives. What can you actually run on that hardware? So what do you need to do? You need to have a rather good understanding of, if you have this sort of hardware, what can I do with it? What will it mean for the machine learning results? And only then you can make the decision also on the hardware to understand what hardware will produce the right cost point, right power budget, right final machine learning results to have the right balance of all things. Another sort of a example that goes quite a lot to the cost budget of things is when you have wide area video analytics. So for example, when there's a huge number of cameras, let's say a few thousand, on a wide area, and there's quite a bit of video data coming through that you need to process. And that means how do you build a tree where you have a hierarchical network that brings in the data from the cameras themselves. At certain nodes of the network, you have actually computation that does early pre-processing, for example, removing any identifiable information from the video, and does other early processing of the data before even more centralizing the data for common analytics nodes. How do you actually balance the hardware on the edges of the network? When do you combine data to larger units together? What's the cost impact of all of that? That's a rather big sort of moving parts question of hardware, cost of the hardware, performance, where you can place it, how much different cameras, how many different cameras can you process per piece of hardware, basically. And the final interesting thing on sort of not going perhaps into the hardware cost itself, but rather the development cost. So, for example, for mining equipment manufacturer, they have around 100 different machines that they produce and sell. Every single one of those machines has, and will even more have, a different set of sensors over there. It's just a cost question, but also a rather practical question to them. And then also every single piece of equipment, considering what is the task that they do, and also what is the cost point of that specific equipment model, they will have different AI-related use cases that those pieces of equipment need to actually support. So where do we end up with it? So there's 100 different machines, huge number of different sensor setups, and all of them need to support different number of different AI models. And all of this needs to run in some random mine in Africa for the next 20 years. So that's quite a challenge, because you can't really do the whole design end-to-end for every single piece of machinery separately, but you need to actually do a design for the AI architecture itself as well, so that you can flexibly modify the compute capabilities so that it's not all, it can actually scale from the sort of low cost point, simple machinery, all the way to the premium machinery where there's so much more models actually running over there with perhaps even totally different sensor setups as well. On the data interaction, one example from the automotive autonomy world. So it's not just let's detect a bunch of cats and trees around the car, but it's also a question about, okay, what's going wrong with the data? So when you have a bunch of cameras, LiDAR, and so on attached to the car, then, well, a car is not a rigid piece of metal. It's made of steel, sun is shining, and metal expands. And when the metal, the steel in the car expands, that will actually move also the placement and the direction of the cameras installed to the car, meaning that those will not be calibrated anymore, and all of the machine learning that you spend so much time to make work will fail. So what needs to then happen is to have real-time calibration of the cameras constantly done with machine learning itself. Basically having machine learning monitor the data coming from all the different sensors and modify real-time the calibration configuration to make sure that everything's still functional. Skipping on to the last over here for the smart device imaging stack. So over here it's a question of a rather popular set of laptops. So there's quite a bit of, once again, various processing functions you need to have running around the camera. It's not just about let's do funky stuff with the camera, but it's just like really simple basic image processing to even have a image, a video of any kind come to the screen in a Zoom meet, for example. And then it's a question that there's a bunch of, once again, bunch of chipsets. Some are part of the camera, some are part of the laptop in general. And then there's a whole bunch of different computation. Some of that can actually be shared also across the basic image processing. Some of that is specific to AI. And as you know, generally deep learning methods, they work far better the less you do pre-processing. In general, you generally use that, make things just more fragile and harder to actually run in production with that. So what is the right combination of, okay, this is the basic ISP path where I'm not going to do any AI, I'm just going to do this computation on this specific hardware. And here's the other AI stream where I'm going to do a bit of additional compute as well. Where do you put the computation at each point so that you make sure that the results actually end up on the user screen with low latency? On the operations interaction, a few examples here as well. So machinery control. So when you go to a huge cruise vessel, they cost $1 billion. They consume 100 megawatts of power, and they support 10,000 people on board. So there's quite a bit of machinery that are consuming power at 10 megawatts, 20 megawatts range. And if you can actually go and save a few percentages of that energy, that's quite a bit of money. Also, that's quite a bit of CO2 you don't need to put into the air. So there, naturally, when you have high power machinery in question, you really need to pay attention to how do you wrap AI control models with sort of safety-focused code to make sure that certain constraints are not broken during the operation, to make sure that it actually stays efficient, it stays within the documented range of operation for the machinery, and it's actually predictable also from the shore side. For the vessel autonomy case here, it was an interesting case because it's a combination of edge and cloud. And then there's, as part of the overall autonomy stack, on the sea side, where there's intermittent network connection. It's sometimes available, sometimes it's not. And also, sometimes things are, you really need to do them right now, but sometimes things are, okay, let's see, we can actually maybe do this computation a bit later. And then it's a question, okay, what are the bits of computation? What are the bits of use cases that you're going to do on the edge side? What are the bits you're going to do on the cloud side? And perhaps what are the bits where you're going to do a piece of the computation on the edge, and then you're going to move the rest to the cloud and do the rest over there. For example, just to cut down on the bandwidth, you need to use the network because that's rather expensive once more. And the final rather different kind of question of, okay, how does the AI decisions affect operations in electronics manufacturing? So where there's PCB scanning, so printed circuit boards, and well, that's the picture over there. And then, well, sometimes the PCBs are manufactured in huge volumes, so millions and millions of them. But sometimes, for example, over here, it's more of a question, you're going to manufacture 50 of them. And you're not going to build a specific AI model for every single separate board where you're just going to have 50 examples of them ever going through before it gets replaced with a totally different pattern. But right now, it's basically human work to do all the scanning and make sure that there's no errors on the boards. So there's quite a bit of potential to automate things. And then the question is that, okay, if you're going to constantly, every single day, switch the board pattern that you need to be testing, but you're also going to be creating new test points in the factory. So today, they were testing the boards at that piece of the whole production cycle. But then today, we actually feel that that part of the whole process is working pretty well, but we don't know that much about this. So we're going to actually go and set up a new testing deployment, of the quality testing deployment at this point of the overall production process. So how do you make sure that you can actually go and bring it up, the whole new deployment, including also for different patterns, with cost effectiveness? That's a rather critical question where you really need to think about, okay, what are the type of model that you can actually go and put into production in this kind of a situation? How do you, for example, augment the data? How do you otherwise make sure that the data, that the model is still functional when the incoming data is rather different from a different deployment, different environment, different lighting around it, and so on. So the final bit on the is going to be on the MLOps. So I think overall MLOps has become this sort of a big word everyone's talking about during the perhaps even just the past year or maybe past few years. So there's been quite a few projects where we've been building MLOps for rather big European companies as well. So first of all, of course, it's a question, okay, why do we have MLOps in the first place? And then once we understand that, then we can go and answer, okay, what will MLOps for the edge look like? So briefly on why do we have MLOps in the first place means things like, okay, it's about the efficiency of the learning loop. So when you develop AI, it's often about explore this unknown jungle. You don't know where you're going to end up, but you sort of know that, okay, you're probably going to find your way through it. And then it's a question, how quickly can you do progress? Learn things across the technology stack to understand how to have the overall thing working. Well, we used to already have DevOps in the past. Well, it's still a thing. It's a rather big thing and still becoming more industrialized. But then actually, why can't we just use DevOps is the fact that with machine learning, it's not the human that is writing the logic. So there's no code that you can go and read and say, okay, this is what the solution does. But what is deciding the logic is the data that you put into the model itself. So if you're going to do an audit for a machine learning solution, it's not the question of let's review the code and see how it works, but it's rather the question of let's review the Teradata of really complex data and see what's contained in that. And that is actually a rather open research question still. But nevertheless, MLOps is naturally, that's the reason why we have MLOps. It's a totally different thing to understand the logic itself within machine learning. So what does MLOps for the edge look like? There's totally different kinds of answers to the rather similar questions. And for example, when we go and talk about MLOps, generally for customers, it's the first thing. You probably don't need it, because usually MLOps becomes relevant only once you actually have somewhere like 10 models, for example, in production. There's been some where there's already 100 models in production at our customers. But then the other point is that there's quite a bit of difference. How does these questions actually then turn themselves into reality when you move to the edge side? So for example, instead of looking for where do I find the specific data in the cloud world, how do I put those as part of the overall data flow, then the edge question is rather on the side of how do I detect when the data flows change. So for example, if you have a bigger industrial operation ongoing, you have AI running there, there's constant changes going to the automation system, to the sensors, to the cabling in the factory, and all of those things can actually go and do something weird and break your machine learning over there. Another question on the cloud side, it's a question, okay, you have this model, and from there we develop the next version of the model, and from there we develop these two different types of models. But when you go to the edge side, it's more of a question, where do these models actually run? So it's not the evolution of the models, but it's the evolution of the overall device and models hierarchy that you have in place. If you look into the features of AI models, so on the cloud side, it's more of a question that, okay, do you have a feature store where you put a bunch of features and then decide, okay, what are the features I'm going to use for these models? But actually, in the edge world, where there's always a resource constraint in place, you need to know how do I actually have the same hardware run one more model. Then it's often more of a question, can you actually do a kind of a embedding, for example, neural embedding, at which you're sharing a certain middle layer of a network, and then use that as a basis to run multiple different deep learning models all the way to the final end. For a final example here is on the AutoML packaging. So on the cloud world, it's often it's more of a question. Okay, let's just use a huge bunch of compute to decide what is the optimal model architecture. But more on the edge is naturally, well, you don't have infinite compute, so instead you need to have sort of more like just really good engineering understanding. How do you need to adapt the specific model so that it fits the specificity of that hardware in question? So with that, I think like the last bit is simply just to repeat what we already had. So Edge AI, while there's quite a bit of research ongoing still there, it's already something that we do a lot every single day for a lot of different use cases. There is actually this underlying structure that we use all the time. So it's hardware, data, software, specifics of modeling the AI, and then how to run things in operations. And the big thing there is that if you're going to go and put AI onto the edge, it's not enough to deal with the AI problem as separate from all the other technology, but you really need to think of it end to end. What are the actual interaction that goes on across the stack from AI and back to the AI decisions? So with that, thanks. Any questions?
Okay, so does have anybody a question? Yeah. Okay, so I have a question for you. You said that you were really interested in state-of-the-art technologies and that maybe half your employees hold PhDs. Yeah. So my question is, do you also do research in your company?
Well, there's a lot of people who do sort of part-time work at Silo, and then they do part-time, for example, postdoc on the side. So that's actually pretty common. And then there's once in a while always there's people who get the research idea and then want to do publications. We do support them overall, but we don't systematically do research ourselves. But there's sort of quite a lot of activity. There's around 10 professors over there as well. We do run weekly research club and so on to really go through their latest in research.
Thanks for the talk. So you do hardware and software, right? You develop both at...
let's say like we're 5 years old, so there's limits to how far we have sort of have time to evolve in that time. So I think like we really started from the AI model world itself, like really doing the science bit of modeling, and then we sort of expanded elsewhere. Partly with really this realization that you can't just do the model and you can't just do the software, because even then if you do just those bits, then there's the hardware team somewhere else in the customer organization, and they are doing things that really affect what we are doing, and what we are doing is really affecting what they are doing, and right now we aren't really talking with them enough. So then that was sort of natural conclusion that we really need to know, we really need to be able to talk with them. So we don't sort of like, if you think about build actual tangible hardware, that's not the case, at least at this point in time, but we have a whole bunch of people who are really good at the hardware bits. So we really can do all the way to the system on chip design if needed.
Okay, thanks. And on the software side, you mentioned TensorFlow Lite as a framework, right? What else? Is that what you're using, or are you also working with PyTorch, or what are the kind of frameworks that you...
Yeah, I think like whether it's PyTorch or TensorFlow, it's sort of like everyone makes their own choice most of the time. So it's a question of preference and sometimes also flame wars in the Slack. Yeah, like TF Lite is definitely just one option. So it depends so much on these various questions. So I think like if for some hardware, there's like a really clear end-to-end software stack available there. For example, if you do stuff with Qualcomm, they have a pretty good end-to-end setup. Same for Xilinx FPGAs. There's actually decent library support. Intel Open, we know, is one again. Huawei Ascend is actually pretty good nowadays as well. So it depends on, okay, where do you break things down? Sometimes you can actually do everything with the hardware-specific stack, but then sometimes, for example, if the performance isn't that totally critical, it's more about the productivity, like how quickly can you do the things, then it's probably easier to sort of like use the hardware-specific stack of software for a bit of smaller part of the solution, and then use like TensorFlow Lite for the other bits, which are sort of closer to the developer. So it really depends.
Yeah, thanks a lot.
Okay, I think we move to the next presentation. Okay. Thank you, Niko.
Just final note, so I need to step outside for the next call, but I'll be around today and tomorrow, so if you have other questions, I'll be around. Thanks.